Hello and welcome to Spectroscopy with me, not a doctor, sorry about that, Finn Attenborough Sutty, accompanied as usual by my trusty colleague, George Lewis.
In the previous lectures, we have covered atomic emission and absorption processes, atomization, the Boltzmann equation, Beer-Lambert law and UV-Vis as well as calibration. Now we are moving on to other spectroscopic instruments, firstly looking at ATF-TIR spectrometers, building on what you've learned from Dr. Hanley, then Raman spectrometers and fluorescence spectrometers. If you are still struggling with FTIR, I suggest you follow the link to find out more or review previous lectures notes on now.
To begin with, optical path length differences, or delta P. This is the difference in length of the beam path reflecting off the stationary mirror versus the moving mirror. The path length can be worked out using the equation on the screen, where px is the path length of one of those beams, b to mx is the distance from the beam splitter to one of the mirrors, and nx wavelength is the distance expressed in a number of wavelengths of light of a given frequency.
The reason for the 2 in the middle part of the equation is because the slit beam travels from the beam splitter to the mirror and then back to the beam splitter. You'll end up with 2 values, one for the stationary mirror and one for the moving mirror. Therefore, delta P can be calculated using the equation on the screen, and if delta P over lambda is an integer, then the beams are in phase. But if it ends in 0.5, then the beams are out of phase.
We would talk about interferograms, but due to our combined lack of knowledge in this group, instead there is a video we want to show you. Moving on, Fourier series. Any periodic function shown in the top right corner of this slide can be deconstructed into a series of sinusoidal waves, or the sine wave, which have different frequencies and amplitudes. The individual waves can be summed together to get the organic period function. The Fourier transform, a clever mathematical tool, works out all the sine waves that you would need to sum together to get any periodic function. It tells you the frequency and amplitude of all the signals that you would need to add together to get the periodic signal you have recorded.
Data from the analytical instruments is too big to calculate the Fourier transform by hand, as seen by the equation in the top left corner of the screen. It is always done by hand and is built into most programming languages. The Fourier transform programming takes the original signal and converts it into a spectrum showing the frequencies of all the spectrums making up the original signal, this being made easier to see with amplitude versus wavelength.
Dr. Kilgour has kindly converted this to wavelength to make it easier to see.
Cheers, big man Dave.
Moving on to total internal reflection. The refractive index, N, is the relative change in the speed of light in a given material. This causes light beams to bend as they move across a refractive index boundary. This is expressed in the equation. Oh, they just need to read the equation, the dumb fucks. At the critical angle of a given object, a beam of light will be refracted along the phase boundary. Yay, physics! I was really sarcastic.
Any angle beyond the critical angle will refract the beam of light back into the object, causing total internal reflection. TIR can also occur if the medium the beam of light has a higher refractive index than its surroundings. Examples of this occur in acrylic blocks and optical fibres.
The Heisenberg uncertainty principle is the theory they use to find and locate... No, delete that bit. The probability of locating a photon in a given area. At the point of total internal reflection, there is a small probability of finding the photon outside of the material. This is known as an Everson's wave.
The probability of finding the precise location of the photon increases closer to the phase boundary, as shown by the graph in the bottom left corner of your screen. But by 1 micrometer distance, the probability has dropped off, setting up an ATR FTIR, an attenuated total internal reflection FTIR. An ATR FTIR consists an ATR crystal with 2 curved mirrors either side of it. on the right of a detector and on the left of a Michelson interferometer.
Total internal reflection occurring inside of the ATR crystal means that the beam of light goes to the detector and comes from the interferometer. The ATR crystal is made of a material that has a high refractive index and is chemically inert, usually diamond. Because of this, samples in solution can be placed directly onto the crystal.
The beam of light that runs through the crystal then loses photons due to the bonds in the analyte molecules absorbing the evanescent light. However, crystallized samples are mostly too far away from the surface to absorb any light, and so a metal anvil is used to force the crystals against the ATR surface, meaning they are now close enough to absorb the light.
Now we will talk about the method of operation. Molecules with covalent bonds, which have less of the wavelength, reaches the detector, and therefore they give a weaker signal in the spectra. The probability of a photon being outside the crystal is small, so the results may not be 100% accurate. To reduce this uncertainty, they use very thin crystals to increase the chance of a photon being outside of the crystal.
Over the next slides, we'll be discussing the advantages of FTIR, starting with Cohn's advantage to do with resolution. Before using the ATR FTIR, it is possible to change the setup in order to calibrate it. We do this by adding a helium neon laser and a laser detector. The laser light produces an interferogram the same as the proband source, but only produces one wavelength. So the interference pattern in a cosine wave, the system can count the spacing between each peak. Each peak is very similar to each other, and so this suggests that FTIR spectrometers is highly precise and accurate.
The next advantage that we will talk about for FTIR is that of Jacquino's advantage, which is to do with sensitivity. From previous lectures, we know that many modern spectrometers use a grating instead of a prism, which splits up the colours like reflections from a CD. Changing the angle of the grating allows the detected light to be scanned or selected. This is also done using a computer-controlled mirror. The resolution of a spectrometer describes how narrow the peaks are. Narrower peaks mean better accuracy on peak position, better ability to tell apart closely spaced peaks, more confident matching of library spectra. However, narrower slits means less light gets through, which results in poor sensitivity. We all love a tight narrow slit. The options then are to either use wide slits and record the spectra quickly, or use narrow slits and record the spectra slowly. From earlier on in the lecture, we know how an ATR FTIR works. There are no slits in an ATR FTIR, therefore all of the light for the source can be used for the spectrum. Compared to a dispersive IR using the same source, an FTIR can provide higher resolving power than a dispersive IR without suffering from poor sensitivity.
The final advantage of the FTIR is Felget's advantage, which is to do with signal to noise ratio. The bottom graph is the better of the two. No shit. As it is cleaner due to less random fluctuations between the peaks. All results have background noise in them. However, averaging the same signal multiple times can reduce the noise. This would be the same if only one spectrum was taken. As you can see, it's hard to see where the second peak is and what the peaks are. After two spectra are taken, the background noise has been significantly reduced, but it is still not good enough to use as reliable results. As you continue to take more spectras, the signal continues to get better until it is sufficient to use as the final spectrum. In an FTIR spectrometer, the wavelength is measured for the entirety of the collection time, so that the signal to noise ratio is significantly reduced in comparison to that dispersive IR spectrometers, which only measure wavelengths for a small fraction of the total spectral time.
And now the benefits of ATR. ATR can analyse opaque materials. Only very small quantities are required for analysis. It is much easier to use, no KBR discs or no noodle. It's very easy to clean, you can just wipe the crystal clean.
We're now going to talk about portable instruments. The ATR FTIR can be made very rugged. Portable versions are now available. These can be used for identifying such things as explosives, drugs, poisons, precursor chemicals, chemical spills, and they can be used by the military, police, fire brigades, etc. Looks like all the uni students are absolutely screwed on a night out then.
And now on the slide you will see a list of all the things that you should be able to do after listening to this lecture. But realistically, you won't be able to, because if you were anything like me last year, you'll have been struggling to stay awake this entire time. And now you can leave back to your beds.